All right, welcome to Physics 3030, the universe, and this is lecture 10, and today we will be talking about general relativity and black holes. Okay. We're not going to cover special relativity here, but there are other resources for you to take a look at for those things. Okay, I'm going to approach this lecture a little bit differently from past ones. There won't be as much of me drawing. There'll be more slides. And we're going to start off with a little bit of gravity history. Most of you are familiar with Sir Isaac Newton here and his contributions to science. His law of gravity was really the first great physical law. And of course it said that attractive force between masses falls off with distance squared, and that force, a change in that force, was transmitted instantly. So we knew right away from any distance that something had changed, right? Einstein knew that this was incompatible with special relativity, okay? And special relativity says that nothing can move faster than the speed of light. Okay, that's what really this is telling us, is that nothing is greater. There's no velocity greater than c. That just does not happen. Okay, and so Einstein set about trying to remake this gravity, trying to mix Newtonian gravity with his theory of special relativity. Okay, and so here I want to do a little bit of a GR overview. Okay, and by GR overview, I am not saying G and R, right? So we're not doing a Guns N' Roses overview. We're going to talk about general relativity. Okay, and this guy, who also has just as much hair as all of these folks. And the overview of general relativity is that we have space-time. That's what special relativity gives us. This is not just space, not just time, but now we put them together to make space-time. And the idea of flat space-time is that something just moves straight as I go through space. I throw a ball across flat space-time, it just keeps going in a straight line. Okay, but if I have a mass in space-time, then it curves the space-time. And so the idea here, right, is that the mass itself curves space-time, and that curvature makes things move in a different path. Okay, so I put a ball in there again. Now I'm starting to have something kind of orbit around it. That first one made it curve around. So the mass in the center here curves space-time. And special thanks here to Shane Larson from Utah State University in Logan for giving me these these videos of his curvature table, his space-time table here. Okay, so this big mass curves the space-time, and then this ping pong moves in a different way. And if I give it even less energy, then I can get it to actually orbit it. So let's see. Get myself to move to the next. Okay, so if I give it even the right amount of energy, I can get one of these balls to orbit the mass, right? And that's exactly what's happening, sort of exactly what's happening when we talk about the curvature of space-time. Now, this, of course, is an inexact analogy, right? Why? Because we have to use gravity to make this mass here is falling down because of gravity already. So that's what's really curving this, is the mass of this pulling against the mass of the Earth. So it's sort of this in an exact analogy here, but it gives you the idea. It's the curvature that makes things move around. Okay? So here's the gist of it. Matter tells space how to curve. Space tells matter how to move. Okay? And not just matter, not just matter. But also light. Okay, and that's what this picture here is that you got the big sun in the middle, okay, and the Earth is here, us observers, and there's some star from behind the sun, and as the light comes around, it actually moves along a bent curve. Okay, so even though this star A is behind the sun, behind the edge of the sun, we can actually see it here on Earth because it's curved around, but it looks like it's coming from B because we assume light moves in a straight line. Okay, and so light has to travel this path as well. Now this is different than anything that would Newtonian gravity would say, because a photon doesn't have any mass. If this thing had a mass and Newtonian gravity, yeah, it would curve around the sun, but photons don't have mass, so they shouldn't curve in Newtonian gravity. But since they just have to follow this path in space-time, then that's how they have to move. They have to follow that curved line. Okay, and so in practice, we see two things that were tested about, that general relativity got tested early on. One was that, to Einstein's surprise and excitement, general relativity describes the advance of the perihelion of Mercury. The idea here is that Mercury orbits the sun in some kind of ellipse, as we talked about before, and that ellipse, this major axis of the ellipse here, actually rotates around the sun. Now, this doesn't happen in Newtonian gravity. Okay, we don't see this in Newtonian gravity. There's a little bit of advance of the perihelion, that's what this axis is called, from the perturbations from other planets and whatnot, but there was still some amount of this advance that was not described by anything else, and Einstein used general relativity to exactly predict how much of the advance should happen. And then this idea that we were talking about earlier in the last picture is called gravitational lensing, right? You have something from behind a gravitating body, and it starts going in a straight line, and then it starts to curve around, right? Well, if I have that happen sort of in all directions, right, I get something focused at some point here. That's why we call it gravitational lensing. In this picture over here, there's some star in the center, and there's a star or a galaxy behind it, and all we see are these rings around it, okay, because the light is coming from the star and kind of curving around, okay, just like this picture is. You can imagine that if I was looking at this from the Earth, this might look like a ring from all different sides. These are called Einstein rings. Okay, so this predicts gravitational lensing. And Sir Arthur Eddington went off in the early part of the century to prove this. He had to look for gravitational lensing when there was an eclipse, so you look for a star just on the edge, and you see how much it's moved by. And he did a number of measurements, and only really one or two of them corroborated this gravitational lensing. So it's pretty interesting little bit of history, because Eddington really believed that it happened, and Einstein knew it was going to happen. And so Eddington just sort of threw out the experiments that didn't make it happen, which is a really, really interesting thing. It turns out when you do more measurements that it is true. Just the equipment at the time was sort of on the edge of being able to describe all this. All right, let's go to the next slide. And then, so there are some surprises that we see from general relativity. One that we're not going to talk about very much today, but we will talk about in the next lecture, is gravitational waves. Okay, and gravitational waves are actually the rippling of space-time. That's what these ripples are, the ripples of space-time. Okay, and we'll talk about that more. And then the other surprise is black holes. Okay, And black holes really have to do with something called an event horizon. Okay? And we'll talk a little bit about that. And the event horizon sort of defines the extent of the black hole. Okay? So, let's get into it here with these black holes. What is a black hole? It's a compact object with high escape velocity. Okay? What do we mean by escape velocity? Escape velocity is the speed that you need to be shot off of the Earth, off of some object, speed to escape gravity. This is not like shooting something off in a rocket. It's like shooting something out of a gun. What is the speed I need to shoot a bullet out of a gun so that the bullet escapes the hold of the Earth? And it turns out that it doesn't matter whether it's a bullet or a person or a rocket or, well, not a rocket. Rockets have an engine attached to them the whole time, so that's why they don't work. But I can shoot anything out, and it doesn't matter what the mass of that thing is, turns out. It's just what the speed of it is. Okay? And here are some typical escape velocities. This is the escape velocity of the Earth is 11 kilometers per second, right? That's 11,000 meters per second, okay? Which is, let's see, we double it about, so that's about 22,000 miles per hour. So it's pretty fast. You have to shoot something really, really fast. Now, rockets don't move that fast because they have an engine that's continually moving, pushing them. This is what I would have to shoot that rocket out of a bullet at to get it to escape. So that's already fast. That's even faster. So with something that's the size of the sun, it has more gravity, so it takes even more velocity to escape the sun. And then there's something called white dwarfs, which are, notice that white dwarfs and the Earth are about the same size, okay, but a white dwarf is much denser, okay, and it's made of mostly neutrons and other neutral particles that are really, really dense. And since it's so dense, it takes a lot faster to go. And all a black hole is something that's so dense that it takes the speed of light for something to escape. Okay, so you have to be going the speed of light to escape this, to escape a black hole. That's the idea of what a black hole is. Okay. And this idea happens in other media as well. Okay, there's some speed at which waves can propagate, right? So if I'm in water, that's what this picture is. I'm a little fish, and I've just sort of gotten washed over a waterfall. Okay, the water's all flowing this way. And there's some speed of sound in water, right? We all know there's a speed of sound. You break the speed of sound, you get a sonic boom, things like this. And these waves, they can only move so fast. But if this water is moving faster than the speed of sound, then these waves, they'll never make it past this point. They'll never make it past some point. There's some point here where that's what this dashed line is, some point here where the water speed is faster than the velocity of sound. Okay, so this poor fish's cries for help never make it back over. Okay, maybe a more appropriate thing would be like, watch out, trying to call to the little fishes that are up here, right, that are about to swim over the edge of this waterfall. So trying to call and warn those guys will never happen, because those waves will sort of build up on the edge here, because they can never go faster than that. So that's another way I like to think about this. Okay, so I want to take an aside here to make an important point. And that is that black holes, it's not about size. It's not how massive something is, but it's about density. Okay? Everything is about density for a black hole. So it's the density that matters. Okay? So I could have a black hole from any size object. I just have to squish it into a tiny, tiny radius. Okay? And in fact, historically, these were predicted in the 1700s. Okay, because people just said, oh, once we started calculating escape velocities, which was done in this period, said, well, I can make something from which light cannot escape. It just has to be really dense. Okay, and many, many billions of times denser than anything that had ever been measured. And so people sort of poo-pooed the idea. But the actual radius for this density that you can predict turns out to be exactly the same radius you get from the theory of general relativity. There's something called the Schwarzschild solution. Schwarzschild, who was the first guy to make any solution to the Einstein field equations. And you get something called the Schwarzschild Radius. And the equation for this is R sub s is equal to 2 big G m over c squared. Okay, and notice that, let's see, G is a constant, C is a constant. G is the Newtonian gravitational constant, C is the speed of light. 2 is a constant as well, just a much more familiar one. And m is the mass. Okay, and this mass is just the mass of whatever I have. If I can squish the mass in, this G and this C basically convert the units of mass into units of meters. Okay, and if I convert those into units of meters, then I show how small something has to be to form a black hole. And how small does something have to be? The Schwarzschild radius for the Earth is about 9, I believe it's 9 millimeters. Okay, 9 millimeters. So take all of the Earth, the giant Earth, and squish it into something that's about 1 centimeter across, right? 9 millimeters is about 1 centimeter across. That is not very big, okay? And that's a huge, huge, huge density, okay? And that's what you would need to do to make a black hole. Now, this does happen in stellar supernovae and all this stuff. You actually get collapse of things into black holes. What happens is that you have so much gravity going on, and there's nothing else that can. It just becomes the strongest force when there's nothing else to hold everything out, like we were talking about earlier. Okay. Okay. Now let's talk about tidal forces from black holes. Now, a tidal force is really just a differential force, so force that you feel differently in two different places, mostly because of the 1 over r squared dependence of something. And the idea is, if I look over at a black hole over here, but it doesn't actually have to be a black hole to even tell this, is that my feet feel a certain force, and my head feels a certain force, right? And because there's some distance here, and because the force is dependent on the distance away, my head feels less force than my feet do. Okay, and that's really what a tidal force is that you feel a different force in one place or the other. Now, you may have suspect from the name of tidal forces that this is actually the effect that causes the tides. It's the moon, of course, acting on the Earth, changes how the water moves because of this differential force acting on the water on the surface of the Earth. Okay. When you're far away from a black hole, it's hard to even tell that you're near one. If you looked at a black hole gravitationally speaking, your orbits would be the same if you were far enough away. It would just seem like you're orbiting around something massive. But it's only when you get really close, right? Really close. So let me draw a little picture here. Okay, if I have some space-time and it's just sort of curved, right? I have something like the sun here, okay, and it's curving space-time. Then if I'm here, it looks like I'm moving around in some kind of orbit. If I have a black hole looks something like this, okay, and where the Schwarzschild Radius is sort of down here somewhere, okay, and if I'm out here, well, it looks like the same thing. I have some kind of curvature. I don't know what's going on. It's only when the curvature gets really high down in here that I start to notice that I'm near a black hole, and it pulls harder on the parts close to it, okay? And this again happens around the sun as well, okay? But around a black hole, especially when you get down into the gut of it here, the difference between those forces is so big that it can have some pretty disastrous results. Okay, and let's see. What happens is it starts pulling so much harder on one end than the other, right? That you get this differential force. This arrow is so much bigger than this other one that it pulls you. It feels like you're getting pulled apart. Okay, this is an analogy for this is getting kind of drug along by your older sister or older brother. You know, you're running and you're actually moving in some direction, but they're moving faster, right? And so they are pulling you because they're moving faster, even though you're moving. It's the same kind of idea. And this will eventually pull you apart. Okay, and this is called spaghettification, right? Because eventually this poor astronaut is going to look like a piece of spaghetti as he gets pulled into this black hole. And of course, he'll have died much sooner than that, right? And one thing that is interesting to note is that bigger black holes have smaller tidal forces. Okay, the tidal force, so this force is proportional to the curvature of the black hole. Okay, and a big black hole, it's the same idea as we were sort of talking about the flatness problem with inflation, right? If I'm on the surface of the Earth, it doesn't look very curved, even though, you know, it's pretty big. I'm sitting here, and it doesn't look very curved to me here. But if I'm looking at a ping pong ball, right, and I look at it, well, I could tell that the surface is curved because it's a lot smaller, and it's that curvature that matters for looking at tidal forces. Okay, so that curvature, if it's really curved, if I'm looking at a really small black hole, that's when these tidal forces are the strongest. Okay, and these tidal forces can be huge. In fact, there was an X-ray burst from the center of this galaxy here, RxJ1242-11. And this is not a picture, this is an artist's rendering of what they think happened. There's a black hole sitting here, okay, and a star came near the black hole. And as it gets pulled closer to the black hole and around it in some orbit, right, it's going to go around it in some orbit, the star is feeling differential forces on one side than the other, right? So I feel some force here and not as much force there, and the star gets ripped apart, right? So this is it getting just mauled by the black hole as it gets thrown around this, and so as it goes all the way around, it just gets broken up into gas. Okay, we saw such a huge X-ray burst from this galaxy that this is what we surmise happened. A star got really close to the black hole and just got torn apart by this black hole. Okay. One of the closest black holes, and the first one that we ever saw, was one called Cygnus X1. And it's in the Cygnus constellation. Cygnus is a swan-looking constellation. Just have some idea of where it is. And this is an artist rendering of what Cygnus X1 looks like. The idea here is that we can see Cygnus X1. This is really important because obviously you can't see a black hole because light's not coming off of it, right? So how do you see a black hole? You see a black hole because of what's accreting onto it. Oh, shoot. An accretion means that I have some companion star, that's this guy here, okay, and the black hole has a gravitational pull. This thing is sort of overflowing into the gravitational pull of the black hole. Now here's the thing though, as this stuff starts falling in the black hole, the gravitational force of the black hole is pulling all of this stuff together, and so it compresses, okay, the material. And this compressed material gets hot, just as we've seen many times before, okay? And that heat gives off, ends up turning into light. And this is a very distinct signature of light, a specific wavelength of light that we can see, okay? And it's Cygnus X1 is actually an X-ray source. That's what the X is for. And we see X-rays coming out of here. Okay. And so that's why we're pretty sure that Cygnus X1 is a black hole. And so we're never 100% on these things, but because of the X-ray source, because we see this star here, we see its companion star, and we know that there's something really close to it, and we see the amount of light given off, and we don't see another star. If we don't see another star, we know there's something massive, because we can tell the mass. There's a mass of this thing and a mass of this thing, and they're kind of orbiting around each other, right? They orbit around each other, and because of this mass, we see some mass here, but we don't see a star. So there's got to be something there, and if it's not giving off light, it's either a neutron star or a black hole, and because of the size of this thing, that's why we think it's a black hole. So these are sort of the games you play when trying to figure out what's a black hole and what's not. Now, one of the most interesting black holes is in the constellation Sagittarius, and it's called Sagittarius A star, and it turns out that this Sagittarius A star is almost exactly at the geometric center of the galaxy, of the Milky Way. Okay, and it's pretty hard to see because we're looking through the bulge of the galaxy, but we can see an X-ray source. Again, we can see radio waves from there, and we can see stars that are orbiting this Sagittarius A star. And Sagittarius A star is actually giving off radiation, these X-rays and radio waves. But again, we believe it's the accretion disk, which is that stuff, that dust that's around, that's getting compressed as it falls into the black hole. And the important piece over here is to see all of this data, right? These dots are where we have observed stars orbiting this thing, okay? And the really cool thing about this is that these are not orbiting in a disk like the planets pretty much orbit the sun in a disk. These are orbiting, and it almost looks more like a atom, right? Like these old pictures of the atom where you have things in all different directions. Okay, and that's because we believe these stars were the stars were captured as they moved by this Sagittarius A star. Okay, and because of Kepler's laws, actually, we can tell what the mass of this thing at the center is, okay, by knowing the mass of these stars and knowing their orbits. Okay, and once we had a closed orbit, we knew with a lot of accuracy what the mass of the thing at the center would be. And this is a really cool video of these things orbiting around. Right, so this is over the course of different years, 2007, 2008, 2009. Okay, and that's what we've seen before. Let's take another look at that. Pretty cool. These are all the stars that we've seen moving around Sagittarius A star. Now, turns out, you look at this data, you calculate what's the mass of this thing in the center. The mass equals 4 million times the mass of the sun. 4 million times. Okay? That's how big the thing at the center of these stars has to be to fit the equations of physics that we have. Okay? So, 4 million masses. There is nothing that we know except for a black hole that could be that dense, that could be that big, right? Here's another picture of this data. And to explain the motion, you would have to have a density of about 35 billion stars per cubic light year in this picture. 35 billion stars. So that would be 90 million. So that was the density, and this is 90 million stars in this picture. 90 million stars in this picture, if this was caused by stars and not a black hole. But obviously we don't see 90 million stars. Okay, so that's how we know that's a black hole at the center of the galaxy. Now these black holes at the center of galaxies we call super massive black holes. Okay. And one way where they could have been formed were these hypernovae from the population novae, from the population 3 stars that we talked about in the last lecture. There are other ways that they could have formed. They definitely could have formed from the aggregation of many black holes. And it looks like most galaxies have a supermassive black hole at their center. And you think, well, how would this happen? Is there a black hole and the stars get trapped around it? Or what way does this work? Well, it turns out that if you take a galaxy that doesn't have a black hole around it and you collide it with one of these supermassive black holes, what ends up happening is there's some big disruption in between, right? That you're not really sure what's going on, and all of a sudden, in the end, you get a galaxy. The supermassive black hole just ends up at the center because of the gravitational well of this supermassive black hole. So you don't have to have them formed around each other. If a supermassive black hole collides with a galaxy, which it's had 13 billion years to do, then the supermassive black hole just ends up at the center and everything ends up orbiting around it. So that's how we think most galaxies ended up with these supermassive black holes. And this is all done in a computer simulation, obviously, to try and do this in some amount of time that we can see. So that's what the simulations tell us. Okay, so done a little bit of an overview about general relativity, and talked about curvature and how curvature affects things like tidal forces, right? And it tells matter how to move. And we've talked about black holes and the Schwarzschild Radius, okay, and some of the neat things about black holes and how we think we know we've seen some, or seen the evidence of them anyways. Okay, so that's it for this week. Thanks very much.